I have the great pleasure of hosting Professor Risto Miikkulainen. Professor Miikkulainen, thank you so much for your time and for doing this podcast.
Yeah, looking forward to it.
Excellent. I would like to start our discussion with your journey into AI. Can you share a bit about your journey into AI research and what first inspired your interest in the field?
Um, yeah, I mean, like many of us in my generation or my kind of age group, we we grew up with Star Trek. We grew up with science fiction, and indeed, 2001: Space Odyssey, HAL. That was my inspiration. I wanted to build HAL, but make it nice. Make it right, do it right, and indeed, other science fiction like that, Data and Spock, Mr. Spock, and all of those that were machines or very logical beings were very inspirational. Then that we could build something computationally that could help humankind, that could work as companions, assistants, and get us further. And of course, this is a big picture. It's a pie in the sky. It's something you might want to eventually get to, but you have to get very real, very concrete, and start from what you can do. And therefore, I studied mathematics and applied mathematics in particular because it seemed like it's a logical way to get started. You build a good foundation, but also it's important to look at other sciences and disciplines. So I took a lot of psychology courses and linguistics and philosophy. All of that actually matters, and it matters now more than ever. It's amazing how we are coming back to fundamental philosophical questions about what is truth, for instance, now that we are looking at LLMs and trolley problems when we have self-driving cars. So I think it was a really interesting journey in that, in my mind, they were all connected, even though they seem very different disciplines, but they all talk about intelligent beings, and understanding ourselves is a good foundation to understanding how we could build something artificial. So yeah, and then of course I started with the fundamentals of the AI at the time, search and logic and probabilistic reasoning, and then took a class where we looked at neural networks in mid 80s, and I was totally hooked because it was clear that we could fix. To me, it was clear that we could fix HAL by using neural networks. There was no logic. There were statistics. There was an intuitive processing that seemed to be missing from HAL and a lot of these machines that were being built. And that was in the 80s. And even so, when we in the 90s started to make some progress, we could not believe what happened. Now, just the last couple of years, it's just the scale up would get us so much closer. We had good ideas. We were ahead of our time. Compute wasn't there. Now it's here. And now the interesting question is, what is still missing? I mean, we have these wonderfully smart machines, but they are not there yet. They are not believable necessarily. They are not trustworthy. They make a lot of mistakes. They pretend to be very human-like, but underlying that, there are many things that are missing that make intelligence work. So it's a new host of questions, and it's a new world, and really wonderful one.
Right, and you basically have a unique interdisciplinary background in both cognitive sciences and AI. How have these fields influenced each other in your research?
Yeah, yes, exactly. Then I think we do have to look at humans as one very positive, successful example of what intelligence is. I mean, what else could we do? I mean, we can certainly use mathematics and engineering and these hard sciences to try to get an insight in it, but ultimately we want these machines, AI, to work with humans, be our assistants, be our companions, work together, and therefore we do have to understand how people work. And there's so much that we still don't know and don't understand. So it goes both ways. When we're building these machines, we gain better understanding also what makes humans intelligent and how we work ourselves. And now it's closer than that than ever. One big picture right now, I think, is that I think it becomes even more compelling than ever before that we look at methodologies from this human sciences, psychology, social sciences, even neuroscience, because they are methods that allow looking at a complex system like a brain or cognition and try to make headway in understanding it, even though we don't really understand the principles underlying, say, neural circuits, even. And that is not unlike what we're trying to do now with these very large models that have billions, maybe trillions of parameters. And it's too large to actually understand every little element. But we could use these techniques that have been developed in human sciences to do that. So I think they are coming closer together than ever before.
What do you think are the main limitations of today's artificial neural networks compared to biological neural systems?
Well, there's many limitations, and we are missing out a lot on even what we know about brain science and neuroscience. We don't have a lot of those in the machines today. I mean, we have most of these neural networks that we are still working with are firing rate neurons. So you have just one continuous value that indicates how strong the neural activation is. Whereas neural networks, they have spiking neurons, spiking events, action potentials. Is that important? Probably is. It has to do with energy efficiency for sure, but they may also be an information processing dimension that we are missing out. Maybe some kind of a binding or common representation. How these representations are tied together. Um, we have also now in brain science what's emerging or has emerged as circuits, resting state networks, and the fact that dynamically networks are formed, activation networks and interactions. We don't quite have that um, um, incorporated either. And also another big dimension is that brains and neural networks, biological neural networks, are always adapting. They're always changing. Now, every experience changes what you know and how you represent it and liaise memories. Versus, say, LLMs are trained once with a huge amount of data and energy and everything, and then they are more or less fixed. We try to maybe add some fine tuning and do clever prompting, but they are fixed, and they have to be because they would go out of whack if we try to continually train them. There's catastrophic forgetting. There are all kinds of instabilities that emerge. So that's very different foundation as well. And there are other things missing, like interactions and feedback. And brain is a very complex system with much recurrency. And we don't even understand whether there is actually some kind of a central executive that manages all these representations. How do representations sometimes fall below consciousness and our awareness, subcortical representations, and somehow they become then cortical, and perhaps we are aware of them? Is there a hierarchical structure where there's then a central executive somewhere in the frontal lobe managing it? So that organization is also missing. So those are all mechanical and computational ideas and organizational principles that we are missing because we've been so successful in just doing gradient descent, you know, and that's great. I mean, we'll pursue it as long as it's fruitful. But these are principles that we should probably bring in one way or another, and they've been around for a long time. It's just been quite difficult. So that's those are real computational ideas. But then at the higher level, um, indeed, there's, I think, a biggest thing missing. If I need to point out one is that these networks do not know what they know. And our computational systems, LLMs, they are reacting to the input and generating really good output, but they do not have a differentiation between things that they make up and things that are and topics and items and knowledge that's based on actual trainings data. Neither can they understand when they are creating something new because they want to generate something new, and it's different from hallucination. I mean, hallucination means that you're trying to claim something that isn't true. It's against your training. Generating new items might be something going beyond your training, not just interpolating between examples that you've seen, but actually generating something new. There are other methods that can do that in machine learning, but these current neural networks aren't really designed to do that. They're designed to imitate our knowledge, our examples, and what we'd like to do is creativity and extrapolation based on knowledge. So that's one big thing that's missing.
Can you talk about the role of creativity in neural network research and how it can help advance the field itself?
Yeah. Well, creativity is fascinating. Obviously, that's what makes things interesting in all of our experience. Now, the current models mostly are trained with massive amounts of data, and then what the models learn, they learn the statistical distribution of that data, and they can create other examples from that distribution. They can sample it, and that's what comes out when you are asking a question of one of the large language models, or asking one of the image generation models to do something. They are combining elements that they already know. They are interpolating between them. Uh, and in some sense, that is also creativity, and there's plenty of that. It's familiar images; we immediately recognize them. It's stories that we can relate to because we've seen many similar ones. Um, but then again, creativity is really interesting in that the really fascinating new things are those that you don't expect, and those that break the rules. You know, that you see maybe it's a musical piece, or maybe it's a movie or story, and there are many movies, stories, pieces of the same genre, and they sound very similar, and they're pleasant because you kind of know what to expect. But every now and then there's something that's completely new, something that's different. It's like, whoa, that is interesting. It goes against the rules that you think are good and well respected, and it becomes something new. And that's what I mean by creative. I mean, even in patenting, like innovation in engineering and otherwise, patent, in order to have a patent, it has to be uh, something that is new, not exist before, but it also has to be useful and non-obvious. And it's in that sense, it creates a higher bar than just creating something new. It also has to be something that is worthwhile, and something that is not easy to come up with. And that's kind of another creation, or another definition for creativity, is that it has to be beyond just new. It has to be non-obvious. It has to be outside of our rules, our experience. Now, so if I can go on a little bit more, because I'm getting building towards something. So there are other methods, like I mentioned just before, that do that, that are actually designed to do that, to be creative. And for instance, evolutionary optimization, which is a field that I've been working on for a long time, um, it is really focused on that kind of creativity. You do have to set up some limitations on what your representations are and what your search space is. But then you are doing search, and you're doing search with a population of candidates. So it's really crucial difference. That's a crucial difference. That in much of the supervised learning and AI we have one individual, and we are gradually improving it. And that means that we are climbing a hill, because we want to make improvements, and they are gradual improvements, so we get on top of the hill. But if you are doing evolutionary optimization, you have a whole population, hundreds, maybe thousands of individuals, and they are all over the place. They are on multiple hills, and even in the valleys, and all over. And we can afford to have many members of the population be not so successful, because we're only looking for some successes that we can find from that population by recombining them, their elements, and mutating them, also climbing a hill. Mutation is small changes, crossover is big changes, or even just drastic random changes. So that mechanism is completely focused on creativity, finding things that are hard to find, finding things you can't find just by climbing a hill that might be somewhere beyond a very big valley, and the whole community, whole methodology is focused on coming up with techniques that make the kind of maximum exploration possible. So there's a wonderful article that came out a couple of years ago where the community got together and wrote a bunch of these anecdotes about things that they had discovered using this mechanism, and it's just fascinating reading how surprising these solutions can be. So they're not just new and useful; they're also surprising. Non-obvious but surprising, and that's what we have to. It's always really great when you write a piece of code, write a program, run it, and it comes up with something unexpected, surprising. that's what really gives you a kick, and that's what keeps you going.
I see. And what would you say? What makes neuroevolution such an appealing approach for AI development compared to, let's say, reinforcement learning?
Yeah. Well, there's nothing wrong with reinforcement learning either. I mean, it's a different technique and has a little bit different background and different goals. Originally, reinforcement learning was about individuals learning during their lifetime, and the metrics that measured how well reinforcement learning was working were counting every trial during their lifetime as part of the reward. And that makes sense for an animal. They have to survive and they have to get better. And that was very clearly the focus of reinforcement learning. Now, these boundaries other between methods have blurred. A lot of reinforcement learning has no interest in lifelong learning. They also try to develop good final results, like evolutionary optimization is trying to. But still, the biggest difference is that there is an individual that you are gradually modifying. So these methods that have recently become really useful, even though some of them were developed in the 90s, like reinforce, but also newer ones like PPO. And so, I mean, they are still modifying an individual and trying to make safe steps in modification and improvement. And that is the fundamental difference, that evolution doesn't care about safety. It wants to be reckless and occasionally find something really fascinating and new and surprising. So if you have a situation where you know pretty much what you're looking for, and then this kind of a continual refinement will get you there. Reinforcement learning is very good at that. Evolution may not be as good at that because it'll making many more jumps, but it might be better at finding something surprising, completely different and new.
I see. And what challenges do researchers face when they are trying to evolve neural networks at scale?
Yeah. Well, that's the business we've been in for decades, and there's been a lot of progress in that. And I think that one of the main achievements, perhaps, was that recognized as a community that this novelty, rewarding solutions that are just different, not better necessarily, but just different what you had before. That is a really big way of taking advantage of the exploration. And then now we are trying to combine that idea of novelty with quality, fitness, rewards, so that we do guide the search towards more promising areas while not losing the fact that we can be very creative. And there's still work to be done there. But I think the biggest, maybe not challenge, but an opportunity that's not really fully realized yet is to take advantage of the compute. I mean, that's what made AI that we know today. I mean, like I said, we had pretty much many of these ideas in the 90s and they were not bad. We didn't have the compute. And then even like transformer architecture 2017, it was great and it did better than some of the other methods in language modeling, but it wasn't yet what it is today, large language models. That needed orders of magnitude more compute. And we went from 90s a million times more compute in the 2010s. And now I think it was another 10,000 or so since then. So this has been a really big boost for AI. And that's something that we haven't taken advantage of yet in, say, neuroevolution and evolutionary optimization. And we should. We should figure out how we can actually take advantage of this huge amount of compute, because there's a good chance that that will allow us to find solutions in a much more substantial new level. And evolution is very well suited for that because it is a population-based search method. So you can distribute everything and take advantage of parallel computing in a way that's even better than something like gradient descent, because you still have an individual that you help trying to improve. Here we have multiple individuals. So let's scale it up. Instead of what we currently have, 100 individuals in the population, let's have a million, million of them. And similarly, take ideas from biology that we haven't really taken yet. We are really impatient in evolution computation. We want every mutation and every crossover to be better, than the parents, that offspring be better than the parents. Biology doesn't work like that. We have indeed million individuals in the population, depending on the species. And we have also neutral mutations. The individuals are not thrown away. They don't die. There are many mutations that are not really improving, or but also they don't kill the individual. And also weak selection. You can have all kinds of problems, but still survive and reproduce. Selection is not as strong as it is in computation. So we should take advantage of that. Have massively parallel populations, neutral mutations, weak selections, and deep time. Do it more like biological evolution, and we might get more creativity. And we are almost there now. We have enough computation to do something like that. And I think that's a great, like I said, not necessarily a challenge, but an opportunity that we haven't taken advantage of yet.
Mhm. And in what domains or areas do you see neuroevolution is will provide the most practical impact in the coming years?
Yeah, yeah. Well, there's any of these domains where we can benefit from creativity. I mean, if we already know what we're doing very well and we want to do refinement, there are other methods, um, but creative domains, and it might be creating virtual creatures for video games or training in virtual worlds, um, and various devices, design of especially where there's behavior involved as well, not just the mechanical design, but how they operate, become robust, optimize multiple objectives. So there's often cost as well as performance. And in physical robots, self-driving cars, there's also safety and maintenance and different conditions. Different you want to drive the car fast and reliably, and there are multiple objectives there which can be addressed by evolution optimization. Um, Now, there's actually a whole spectrum of those. So if we are evolving entire neural networks, their parameters as well as designs, then we are looking at these kinds of applications, some kind of behavior, whether it's a virtual or robot or some kind of device. And those are engineering challenges. Now, we could also go more into the cognition and intelligence and address, especially if we can do the scale up potentially, questions like where does intelligence come from and what are the determinants, and how can we build agents that are intelligent the same way as people are. And that's a little different from just imitating text, because we might have individuals that are more grounded into experience. They might, even have sensors and effectors and interact with the physical world, and therefore have a similar grounding on their intelligence that humans. Not necessarily. I mean, they don't still go to school and get bullied by bigger AI and all these experiences, but it would be closer and it would perhaps be more human-like. And then it could happen. A lot of that could happen in virtual worlds, and that is really, I think, the most exciting opportunity, that where we could also use a lot of the compute to create virtual worlds that are much more realistic and much more in depth, simulating physical worlds and societies even. And then once we have these artificial societies and artificial physical worlds, we could evolve agents that are much better grounded and much more human-like and much more intelligent. And I think that would be the most interesting direction in the future. And indeed, evolution is perfectly suited for that, because we can have millions of these environments running in parallel, and again, millions of individuals, and run evolution in order to discover intelligent behavior. And then it could be a lot of different kinds of decision making in a society. We could try to discover strategies for decision making, like um, well, business, for instance, and but also how to make society more equitable, how to make it environmentally friendly, how to reduce resources while uh, keeping economy going, and better legal decisions, better medical decisions. So decision making in general would could be really strongly enhanced by these kinds of approaches, and I think that's really where we should be going. And this amount of compute that we have partially goes into better search, but it also partially goes into these better simulations, better perhaps surrogate models that allow us to discover these decision strategies that then can be taken to the real world.
And one of your projects you are working on called Creative AI. So basically, focuses on the idea that machines creating new knowledge or solutions. So how close we are to finally achieving truly creative machines, and can AI maybe help enhance human creativity?
Oh yeah, yeah, yeah. So I think that these scenarios where machines, AI, will take over and decide that humans are irrelevant is not really well posed. I mean, that kind of situation isn't likely to happen because we are always developing AI systems in order to make us perform better, make better decisions in the society for us. And there's always a decision maker, human, who decides whether to deploy this decision. And also the humans will have to decide what the goals are. I mean, do we really want to have, you know, how environment that's clean and sustainable development? Do we really address the 17 United Nations sustainability goals? Is that actually something we want to do? Because we can define them and then use, say, evolution search and optimization to find decision making strategies that get us towards those goals. So it's always humans deciding what the role of AI will be, and also humans always working with the AI. They will get better. I mean, just a couple of years ago, the best we could do is use AI to help us write grammatical sentences. But now AI will help us actually express our thoughts a little bit more clearly, in language. So the tools are getting better and the interaction is getting better. And programming, for instance, I mean, used to write code from scratch, even thinking about where all the bits are. And now you think conceptually about what it is that you're trying to um, write the code about, and you'll get a suggestion from an AI. So your thinking is a little bit higher level. And I think that this is exactly, I mean, they are better tools and we are adapting to them and we are getting hungrier and more ambitious in how we use them. So in that sense, I think it is wonderful that we have this opportunity. And it is, of course, a little difficult to say how everything will change, but that is important to realize that um, it's not the case that some kind of a superhuman AI is just going to be dropped into our current society and everybody goes berserk. It's something that is developed gradually, slowly, and we are adapting to it, and we understand our needs. Our needs will change, and we are solving the current problems with better AI all along. Um, so that I think is a very important realization that it's always AI is always developed in service of humanity, and what humanity is and needs and will become will change, and that is really interesting to think about. So a lot of this is actually really visions motivated by science fiction. It's not a bad idea to look at some science fiction. There are people who are creative and they think about possible scenarios. Not all of them are realistic. I mean, Terminator. It's kind of a joke when you have a really good idea. You look around, the Terminator appear because it was so good that we'll create this future. That's kind of a fun joke to think about, but it's not going to happen like that. Um, it will be gradual and we'll change our goals, but hopefully, use also the science fiction and possible scenarios to understand what the possible harms may be, so that we can stay away from them while we are developing the AI, and not as an afterthought, but something that we have actually in mind. It's okay. Now I'm just babbling, but it's really great that our goals and our concerns have matured so that it was just hard to build AI, any kind of AI. But now we actually being successful and we have to think about what are the impacts of this technology because it is actually finally impacting the world. So we have to think about it. And a whole field of responsible AI has emerged. What we still don't quite know is how to do it so that the development, solving of the problems, which are really hard problems, how can we solve the problems while we actually thinking about the impact at the same time? So that's a change in thinking that has to emerge, and it is emerging. And it's actually really wonderful to see that the AI community itself is very concerned about it. I mean, we have lots of workshops and discussions and positions emerging, and they are very resilient. They keep coming back. If somebody, for business reasons, throws them away, they will come back. So I think it's because it's grassroots. It's what people want to do. We want to build AI that's actually responsible, and that's why I don't think it's going to go away, and it's going to become part of AI development.
Mhm. And what would you say are the main elements that you believe a system needs to have in order to achieve artificial general intelligence or AGI?
Yeah, AGI. um, well, yes, this is very interesting. I mean, a couple of decades ago, when we started talking about AGI, the story is that there's no single breakthrough. It will be AI will advance in many different areas, and the technologies may be very different. And it's not even necessarily a very clear productive goal to think about AGI, because we need AI for driving, we need AI for creating stories, creating emails, detecting misinformation on the web. They are all different abilities, and it's perfectly fine to have specialized abilities. They are useful. So what is the purpose of having AGI actually at all? Why would we need it? I mean, uh, when we are building AI, we can make it useful even without AGI. But it's of course a really fascinating. That goes back to HAL and data and those machines and science fiction. That it's just a fascinating question. What is AGI? And it is very not very far from a question of what is human intelligence. I mean, that's pretty much the only AGI that we know. So when we're asking what is AGI, then it's more asking what is cognition, what is intelligence, human intelligence. And I think in that role, this research on AGI is really, really wonderful. And it is productive too now, because we have, for instance, LLMs. And we can start seeing it. Oh, that is actually, they're doing really good job, the way we didn't even imagine we could be doing. But what's still missing? You know, and that asking, like, why is it not general intelligence? We can make a formal question. Why is it not general intelligence? Why does LLM fail in certain tasks and shine in others? Um, and and of course, human performance is some kind of a yardstick, but we can also go beyond that even, but still understand that this generality means that the machine has extracted some fundamental principles of the universe, of the physical world around us, of the social world around us, the society. And the principles are not necessarily that different. It's not that the principles are all different in vision and language and understanding traffic patterns or machines. We're finding now that if you learn about vision, you get better at language. And this principle seems to hold across many different domains. So that is already kind of a result from pursuing AGI, is to understand that there may be some common principles in many tasks and then some specializations. Um, but yeah, I mean, if you have to, again, my philosophy here and kind of a vision is that the one thing that we are missing is this ability to introspect, the metacognition aspect of knowing what you know, that these machines don't have at all. And if we can build that into the machines somehow, then it is possible for them, for instance, to realize that, okay, this is now a new domain. What do I know that might be useful here? It can introspect its own knowledge, and it can evaluate what it knows and what it doesn't know and what's missing, and can maybe even ask for help, look for something in the web. And that, I think, would be then a big step, even in practice, in building something like AGI.
And would you say that it is fair to say that intelligence is more about adaptability than fixed problem solving? And how do evolutionary approaches basically cater to this idea?
Yeah, absolutely. It's about adaptability. I mean, at first it was about specialized ability, like I said, and that's perfectly fine. But I think we're getting a little hungrier, more ambitious about what we want to build. And now this adaptability is the next frontier. I mean, like I said, brains are all continuously, always adapting. Our machines are not. And it could be a very big improvement on these machines if they could do that. They could be more robust, and even in situations where that are unfamiliar, they could survive and get better and learn from their experience. And this is, but it may require very different mechanisms than what we have today. And you asked evolutionary optimization. So now, biologically, of course, evolutionary optimization is at the level of species, like populations, and not so much in individuals. But a really important aspect of neuroevolution, in particular, and many neuroevolution experiments, this is actually a very big running theme in the book that we just finished on neuroevolution. Um, 30 years of work. We're reviewing and including very recent work on LLMs and evolution, neuroevolution. And one of the running themes is that there's actually a very strong synergy between evolution and learning. And it doesn't mean just that evolution gives you a starting point and then you learn. Synergy means that evolution gives you not the optimal starting point, something that's very close to your final result, but a starting point from which it's easy to learn, a mechanism that takes into advance that there will be learning. So the initial, when you combine these in these simulations that we talk a lot about in the book, then evolution discovers these babies that are very far from perfect, and the learning mechanism will get them there. And this synergy is more powerful than trying to evolve the solution directly or try to learn the behavior directly without that kind of optimization. And evolution is, it's not just necessarily a starting point, like an initial set of weights for a neural network. Evolution can also take a role of designing the learning algorithm. No, that's part of the brain too, how it learns. So evolution can come up with a learning algorithm that works really well with the genetic predispositions. And it can also generate internal training, like pattern generator. There's some computational experiments about visual system where internally generated blobs in the visual cortex or in a loop of couple of different areas could generate species-specific patterns that then bias the youngsters towards what their species needs. In humans, that's face detection. So 3 dots, eyes and the mouth. All you need is 3 dots, and you already can. Babies less than an hour old can attend to faces and will attend to faces more. So this is the kind of it's a synergy of evolution and training. Evolution comes up with a mechanism for generating patterns that learning takes on and gives you the right biases. So that's yet another instantiation of this idea that evolution and learning working together as one synergetic system. Um, and I think that we could try to take more advantage of that and use it better in the artificial systems that we create.
I see. And how do you think emotions and emotional modeling can play a role in the development of intelligent systems?
Emotions. That's a big question. Yeah. That is interesting. I mean, how well do we understand emotions to begin with, and what is the role of emotions? I'm not an expert on that. I mean that, and there are people who do understand or try analyze and pursue research on in psychology in particular on that. I mean, it seems that emotions could be a vehicle for taking in a lot of information and summarizing it, and giving you the proper bias. For instance, sometimes you recognize the situation is dangerous, uh, dicey somehow, so you pay more attention. And sometimes you have affect, and affect allows you to work as part of the group, and you might even forego some of your own goals and own well-being for the good of the group. And again, for the species, that can be very beneficial. So I believe emotions do play a role, evolutionary role, in particular. We do need to build those simulations to understand them better. We actually did one really interesting study in collaboration with Kay Holkamp at MSU, who's a zoologist, on hyenas and how they develop this behavior where they can steal a kill from lions, which are so strong that they can kill a hyena just by hitting them. But if there's enough hyenas, 4 times more than the lions, they can act in unison. They can form a team, coordinated attack, leaving lions a way out, but approaching them from other directions. If they do it with perfect coordination, the lions will flee. And we found, I mean, part of it was computer simulation, part of it was field work in actually Masai Mara, um, collecting hyena droppings and finding out what kind of hormones they had, which then mapped to emotions. So we could see that there was an interplay of multiple emotions, including fearfulness. Obviously, you fear the lions, and if you don't, you die. But then there was another emotion, affinity to the team, to the teammates. And then the affinity actually became stronger and unusually strong. And now they acting as a team because they feel such affinity to their teammates that they actually act together and approach the lion together. So there's a very clear role for emotion in evolution. We may be seeing evolutionary breakthrough happening in the hyena species. I mean, they're smart, but they're not that smart. I mean, there are baboons in the same environment that are much, much smarter, but they have developed this one behavior that's more sophisticated than anything else. So in that sense, it might be like the first one, and then there will be others to follow in evolution. And emotions there may have played a very important role, allowing this kind of coordination and teamwork to emerge. And as we understand emotions better, we may find that there are these roles. And then a really interesting question is there still a role in a modern society for something like that? Or would we all be better off if we were Vulcans? You know, so maybe we'll build some simulations in artificial worlds, and we can actually study that effect. We can give them emotions, we can make them logical, rational, and see put them under different scenarios, various threats, dangers, you know, challenges, and see whether emotions play a role and understand them better.
And what are your predictions for the next 5 or 10 years in terms of breakthroughs in AI and neuroevolution?
Yeah, yes. Well, we definitely hope that within that 5 or 10 year time span, we can get a handle of these issues that I brought up, and in particular this metacognition issue. I mean, that is the one that I really want to focus on, and I think it could have the best payoffs. But also, um, I think we are ready to take advantage of some of these techniques in society and deploy them. And there's now a wonderful collaboration between academia and industry that's never existed before. It's pretty much just one community now, and lots of exchange of ideas. And then industry, some of them anyway, they have also access to applications and building applications, and that's why we have LLMs that we can interact immediately. Anybody in the world can. When was that ever a case that you develop cutting edge technology and anybody in the world can use it? I mean, this is wonderful. So I think that we will see more of that. And then, of course, there's the other side that we have to understand the potential harms and how to make it safe and productive for people. Um, but that I think will continue. But scientifically, I think that this metacognition is the biggest challenge. Um, there may be other challenges also in order to deploy AI. We may have to have some solutions on just efficiency and energy usage and sustainability. I mean, we can't put an LLM in a maybe a wristwatch or shoes or refrigerator or something. So these applications may require um, more innovations. And there, for instance, spiking neural network implementations that take much less energy and can be deployed in the edge. Um, they can become a breakthrough. So we can have AI everywhere, but they may require that technology. How do we actually take advantage of spiking neural networks while still maintaining the same kind of a level of performance?
Do you believe that evolving AI systems will help us address the alignment problem, making AI inherently safer?
Yeah, yes, that is a very important question, and it's a good continuation of what I just said. In that, now currently, a lot of these systems that we are aligning using fine tuning, we're trying to make it impossible for an LLM to say anything bad or give instructions that would cause harm. And it's like trying to tie their hands. somehow they would be incapable of that. And I just don't believe that that is sustainable in the long run. I mean, that it's a very productive approach in the long run. It's the metacognition again. I would very much more trust an LLM or AI system of any kind that actually knows what it's doing and knows that this is a question that if I answer it literally, I'm going to tell this person how to build a bomb, and he could go on do something bad. So the AI itself knows what it's doing. It knows that this is potentially dangerous. So I'm not going to give that instruction. I need to understand better where the person is coming from. I mean, there's a role for AI also to create these kinds of harms in a simulation in order to decide how to counteract those harms, for instance. So we do need those agents also for that role, and it should be possible to use them. So again, a metacognitive AI could be more trustworthy, and the alignment problem would then require us aligning our values with them, not preventing them from doing something that they could be doing that could be harmful. So I think yes, I mean it's important to do in the short term so that everybody in the world can use them and we are mitigating the harm, minimizing them. But there's a scientific problem underlying it, and we hope we can solve it and then have much better AI as a result.
And what aspects of human cognition you think machines will struggle the most to replicate?
Right. Okay. Um,
Tough question
well,
once again.
yeah. No. Yeah. Yeah. I mean, no. It's a very good question. So just right now, when you're using AI LLMs, and they're useful in, like I said, coding or you know, writing, and summarization, for instance, in documents. You take a scientific paper, you ask LM to summarize it. Um, they're useful, but they're the challenges that they don't quite grasp the value of like a paper. Why was this paper written? What is the problem they're trying to solve? I mean, sometimes the authors don't know that either, and are not very clear on that either. But usually because it's a paper in the community, people share that knowledge, why this research is worth doing or this point is worth making, and we have that shared knowledge. And LLMs don't quite always get that. They don't really understand the implications and the reasons behind saying things. So if you ask them those questions, they often give superficial answers, and they miss what's really the point of doing something. And that I think is an important part that we still have to supply at least today. Yeah, and there may be others as well.
What advice would you give to young researchers or students who are interested in pursuing a career in the AI?
Yeah, absolutely. It's a wonderful time to be alive. That's what I always say. So enjoy it, and perhaps the most important advice is that don't just focus on what's in front of you right now and what's most exciting, but utilize this opportunity also to explore. So indeed, learn about philosophy, learn about human sciences, neuroscience, cognitive science, as well as these technical aspects of mathematics, statistics. Uh, they are still important, even though the techniques are a little bit more different now that we have to use. But this kind of a broad perspective and broad foundation is where the innovations will come from, where the understanding will come from, and seeing the opportunities for these techniques and AI and integrating them in a safe manner will require this kind of depth of multiple disciplines. So, and now multidisciplinarity is easier than ever because we do have so many resources about it to learn about it. Um, Now, one challenge is that it is like drinking from a fire hose. So there's so much information that sometimes it's a little difficult to filter it out. But again, tools are emerging in that, and we have a lot of summaries and tutorials and materials uh, that allow you to get at least kind of a general idea, even if somewhat superficial. You don't have to know all the technical details, but you understand a high level what some disciplines doing and what they know about, say, ethics of trolley problem or something. And therefore the critical thinking part becomes even more important than ever, to evaluate what you see, because there will be many voices, many approaches, many perspectives, and you still have to form some kind of a synthesis of them and take them as they are, not at the face value, but in context of what the disciplines are concerned about and what their general accepted problems and goals are. Um, and but it's becoming easy. I mean, it used to be very difficult to talk across disciplines. So much so the papers were written about it, how people talk past each other. Even when we tried to bring in biological evolution and computational evolution together, we thought we were communicating. But there was a project, philosophers came to our meetings and interviewed us and listened to us, and they found that we have very different understanding of terms like evidence, you know, something really fundamental. We don't view it at the same manner, even if we really talk and we think we're productive together, even. So realizing that this is a potential pitfall, and it's also a wonderful opportunity because you can take these different perspectives and gain the richness from them. So that's by far I think the most important advice is to not focus on one view, but actually absorb more of them, and be critical in what you're seeing.
And the final question, so what motivates you to continue researching and pushing the boundaries in this ever-changing field?
Well, I mean, how can you not? I mean, it's like it is the most exciting time. You know, we've been successful beyond our dreams, and the new questions that come up, we thought we'd never have to even address, and we have to even define what those questions are. So there's so much to do, and the tools are better than ever, and there's more investment in it than ever, and people generally realize that it's worthwhile, and you can have an impact. You know, you're not just doing write only papers. You actually, you come up with an invention and it can have an impact in the world. So what could be more exciting? Can't stop.
You're right. Wonderful. So, Professor Miikkulainen, I would like to thank you for this wonderful conversation and for your time. So, thank
Yeah,
you
it's
so
been
much.
fun. Thank you.